You are welcome to SK Pass International College. I thank you so much for watching my videos. I will invite you to subscribe to this channel, like the video. Most of you have not been liking the video. I don't know why. You view and go away. Please like the video, share and comment. If you don't understand anything, comment so that I can respond at the comment section. Thank you. For today's video, we are going to continue with the polarization. In the previous video, I explained everything about polarization. In today's video, we are going to continue with some concept of this polarization. We said that polarization is the distortion of the electron clouds of the anion by the cation. We said that under this polarization, we have certain terminologies like polarizing power and polarizability. What is it, polarizing power? It is the ability of the cation to pull electron clouds of the anion towards itself. And when we talk of polarizability, it is also the ability of the anion, the electron clouds of the anion, to move towards the cation. So that is what we said basically. There are certain rules we need to observe when it comes to polarization. And in this case, there is a scientist. We are going to follow the scientist's rule, which is called Farade's rules. Farade will help us with some few rules to understand how to group some of these, knowing the one having higher polarizing power or higher polarizability. Now, without much ado, what Farade is saying that anytime we have any molecule, the conditions for a molecule that is ionic compound to have what we call polarization, there should be. So let's look at this. This sodium chloride, we say is ionic, but it's not 100% ionic. There's some nature of covalency in this. So for this to happen, it says that the cation should be smaller in size, and the anion should be bigger in size. What it means is that this is my cation, and this is my anion having the electron clouds. This should be smaller inside, and this should be bigger before polarization can occur. That is the basic thing. Then, he also explained further that, apart from considering the size, both of them, both cation and anion should have high charge. So both of them should be having high charge. And in this explanation, the bigger the charge, the bigger or the greater the polarization. What do you mean by this? It's vice versa. The bigger the size, the bigger the polarization. The smaller the size, the smaller the polarization. What it means is that, let's assume I have sodium chloride, magnesium chloride, aluminum chloride. In these various compounds, you realize that they all have chlorine in their compounds. The only difference we are having is the metals, that is sodium, magnesium, and aluminum. So what you are going to use is, let's consider the charge of sodium. Sodium is plus, magnesium magnesium is 2 plus and aluminium is 3 plus. And this man is saying the bigger your charge, the more polarized you are. And if you are more polarized, if the polarization is very high in you, it means you are less stable. So it means that when you want to compare this has the highest polarization. There are more covalent nature introduced in aluminum chloride than magnesium chloride and sodium chloride. And remember, in our previous video, we said something about covalent molecules. That if you look at ionic compound, we said for them, they have high boiling and melting point. They can conduct electricity at their molten state and others. But anything you say about ionic bond is opposite of covalent bonds. So when it comes to covalent bonds, we can say that they have low melting and boiling points. They cannot dissolve, they cannot be dissolved in water or polar solvents. So it means that they normally dissolve in non-polar solvents. So these are directly opposite to ionic compounds. And we are saying that anytime there's polarization, we are introducing some covalent characters into the ionic bond. And the more covalent characters introduced into an ionic bond, the weaker that molecule becomes. So it means that when I ask you to arrange the following in increasing boiling point, we can use this same concept of polarization to arrange them by saying this sodium chloride will have the highest melting point compared to magnesium chloride, and this will have the lowest boiling point. So either boiling point or melting point, if you are asked to arrange this, you can consider their charges based on the Faraday rule. Now let's look at another aspect of we call that dipole moment, which we normally represent with mu. So, what do you understand by dipole moment? In our previous video, we studied about this sodium and hydrogen chloride, that it is a covalent molecule. And this HCl, as you see here, is a polar covalent molecule or a polar covalent compound. Now, looking at this HCl, we can say that this hydrogen is partially positive and this chlorine is partially negative. Now, when you look at these two, they have been an unequal sharing of one pair electrons. So what is happening here is that one of the elements here is more electronegative. In terms of electronegativity, this chlorine is more electronegative than the hydrogen. So the electrons will be pulled or will move towards where there is more electronegativity. And that moment or that force moving this to the more electronegative element is what we call dipole. Dipole. So this is what we normally see. You see this sign, it's moving towards the more electronegative element. Now, having said this is moving towards the more electronegative. So you see the sign like this, anytime you see it, it's moving towards the more electronegative. Now, the ability to determine the strength of this dipole is what we call the dipole moment. So, if you want to know the quantity or the amount of this in terms of calculation, we use dipole moment. Therefore, when you're asked to define dipole moment, it is just the product. Okay, the product of looking at this, there's a distance from here to here. So the product of the charge of the distance of this charges is what we refer to as dipole moment. Dipole moment can be calculated, and we normally calculate that in the bar, right? So that is exactly what we are supposed to do. When you classify or move further, we will look at how these molecules are calculated. There are numerical values for that. So basically, that is what we refer to as dipole moment. Now, all this we are talking about is as a result of getting stability or obeying the octet rule. And we have already said in our previous videos that anytime you draw any of these structures, they are represented in what we call the lowest dot structures to show stability. However, for us to end this video, we will only lay emphasis on the fact that there are some rules that are violated when it comes to the lowest dot structure. One of the violations of this rule is what we call the extended octet. Extended octet. Just like we're saying, anytime you draw a lowest dot structure for molecules, it always obeys the stability rule. But there are some exceptions, like PCl5. For instance, the central atom here is phosphorus. We'll have something like this. Fluorine. You realize that this is not obeying the octet rule. So this is an extended octet. I would like you to get some examples of molecules having the same violation of the octet rule, which is called the extended octet. Write your answer if you are able to do it correctly, yes, in the comment section. If you are not able to do that, just write no. And then we have what we call limited octet. It's a violation of the octet rule. Limited octet is not able to get to the standard, that is tetra. They are not having tetravalency. So something like BF3, for instance, can be classified as limited octet because when you draw this will be having only 3 instead of 4. So this is a limited octet. Something like this beryllium will have this, and it's also an limited octet. So apart from this molecule, there are other examples. You have to look out for those examples. Write them and tell me why they are not obeying the octet rule. In our next video, we shall be looking at some concepts which will talk about metallic bonds. We know the strength of bonds, some characteristics of metallic bonds. Read ahead whilst we bring video on that. And under this topic, we are almost exhausting the first aspect or first type of bond, which is interatomic bonds. We have exhausted the ionic bonds, covalent bonds. We will talk about metallic bonds. Then we go to the intermolecular forces, which we'll be talking about hydrogen bonding. We'll talk about dipole. Then we'll talk about the Lambda dispersion forces, where we will be discussing something on dipole, induced dipole. Thank you for watching this video. Subscribe to this channel and get new videos. Thank you.